Alright, here. So we have a problem here where we're trying to fill in the blanks using only prime numbers. Now the goal here is to start talking about primes, product of primes, and how it relates in terms of factors or factorization. There's a prior problem we did, I just want to allude to it quickly, that we were talking about listing the factors of a number. And that's different than finding the product of primes. The list of the factors are all the numbers when multiplied by another integer, and actually in this case a whole number, that could multiply to the desired number, the number that we're factoring. Product of primes is a little different. So the first question is, well, what is a prime number? A prime number is a number whose factors are 1 and itself only. So, for example, 24 is not a prime number because 2 times 12 is 24, so that's not 1 times itself only. 1 times itself does work, but it has to be the only one that does work in terms of whole numbers. So let's see if we can figure this out. So one way to think about this is you could just divide by the numbers you have so far to figure out what's left. So let's look at that. So 210 divided by 2 divided by 3, 35. So I have 35 left, and I'm looking for prime numbers that multiply to 35. Well, we could think of this as times 1 times 35, but the problem is 35 is not prime. So what are the factors of 35? Well, we have 1, 5, 7, and 35. So the product of primes that works is 5 times 7. So this would be 2 times 3 times 5 times 7. And this is a prime factorization of 210. Whereas in a prior problem, we looked at the prime factors, or the factorization of 210, and it was all these numbers. Although those are all factors of it, the prime numbers, when multiplied together to equal 210, is 2 times 3 times 5 times 7. B, now 2 with the 6 as an exponent, for those that don't remember, this is saying 2 times itself 6 times. That's what the exponent represents, repeated multiplication. And so this is 4, 8, 16, 32, 64. So this is saying 192 equals 64 times what? And again, we're looking for only prime numbers, so I can divide by 64. And if you're thinking algebra, sort of, if you haven't seen this before, you will assume these divide as 1. This divides as 192 divided by 64 is 3. So this would be 3. So the number I'm looking for is 3. 2 to the 6 times 3. And you'll notice we try to write them in order from the lowest number to the highest number. It's easier to keep track of. So now on this one, 2 to the what times 3 equals 48. Well, let's divide everything by 3. So here we have 16 is 2 to the what. Well, you can play with it if you want. Or 16 is maybe one you know. But you can think of like 2 times 2 times 2 times 2. So there's 16. So I did it 1, 2, 3, 4 times. So it'd be 4. So what I'm looking for here is 4. Now, the exponents don't have to be prime numbers. If you really wanted to do that, you could, in theory, write this as 2 to the 2 to the 2. Because 2 to the 2 is 4, and 2 to the 4 is 16. But no need. The exponents do not need to be prime. Last one, 17 times what? 1. 17 is a prime number, because its only factors are 17 and itself. So this is called prime factorization. So we're going to do the prime factorization of these, and I'll show you a couple techniques. One way that I often see students is this tree. And so what they look for is two numbers that multiply. And so many people see this ends in a 2, and they'll say, oh, it's 2 times something, and they divide by 2, 206. And then and this is 2 times something, 103. And now they're like, okay, 103, is that prime or is that not prime? And so you go down the list, you start dividing 103 by things you think might be it. Well, it's not even on the end, so it's not 2 or 4 or 6 or 8, any of those, or 10, because it doesn't end in a 0. So none of the even numbers. What about odd numbers? 3, well, the sum of that is 4, which is not divisible by 3. So it's not divisible by 3, which means it's not divisible by 6, which we already knew. Not divisible by 9. Does 7 go in? You do a quick division of 7. So 103 divided by 7. We know it's not 5 because it doesn't end in 5 or 0. 7 doesn't work. 9. Actually, we already tested 9. So 11. Nope. 103 divided by 13. We're just marching up prime numbers now. 103 divided by 17. Nope. So this is the factor tree. Now what do I do with it? I look for the fruit at the bottom, and that becomes my product of primes. So this is 2 times 2 times 103 if you want to write it in expanded form, or if you want to write it in exponential form, be 2 squared times 103. So you should know the difference, expanded versus exponential. And so we can do the rest here. 13 is just 1 times 13. So this is 1 times 13 is the product of primes. 56. So 56, I think of 7 and 8. I think of 8, I think 4 and 2. 4, I think 2 and 2. And so the fruit at the bottom of my tree are 3 2s and a 7, which I could write as 2 times 2 times 2 times 7, or 2 cubed times 7. Either way, exponential or expanded. The last one, 128, I see 2 times 144. 144 I know is 12 times 12. You might see it as different things. These trees don't have to be exactly as I have them. You might see different things. The key is that you keep going until you have only prime numbers at the bottom. 3 times 4, 2 times 2, and this is the same. 3 times 4, 2 times 2, and so the fruit at the bottom, 1, 2, 3, 4, 5. Don't forget that 3 buried in there. 6, 7. So I have 5 2's. So this is 2 to the 5th times 3 to the 2nd. And you'll find the exponential is a little more compact to write. So key things to think about here: the product of primes can be found through factor trees. A prime number is something whose factors are only 1 in itself, and you can do prime factorization to find the product of primes, either in expanded form or exponential form.